We will be starting the session 1, heterogeneous integration. We have plenty of good seats at the front. Would you like to come and take a seat? And we will start on session 1. I would like to introduce our first speaker for session 1, heterogeneous integration. My name is William Chen. I'd like to introduce Bob Patti. Bob Patti is the president of Nhanced Semiconductor Incorporated. He has spearheaded the development and delivery of cutting-edge 3D and 2.5D integration technology for high-energy physics, medicine, automotive, military, high-performance computing, and other fields. He has managed hardware engineering teams for a number of organizations, and including successful startups. Bob received the 2009 Semi Award for North America for his pioneering work in 3D IC. Remember, 2009 in 3D IC. And 2015 3D Insight Individual Achievement Award. Bob?
Good morning. So this morning I'm going to go through from the impetus of why we're doing integration. Nhanced is a spin out of Tesron. I've been doing advanced packaging since 1999. We built our first 3D device in 2001. The first active device we demonstrated in 2004. So it's an overnight success. So how did we get here? It's because we're really at the effective end of Moore's law. It's not that we can't make transistors smaller, we can. You know, Intel has announced the 1.8 nanometer node. It'll take me about 10 years to start saying angstroms. It took me about 10 years to say nanometers instead of microns. But the problem is the cost per transistor is going up. The development cost is going up. We have effectively shut out most of our industry because the cost of doing business is simply too high. Well, what does this mean? I'm a model railroader, so I like trains, and to me, there's a perfect metaphor here. Near the end of the steam the steam locomotive era, the industry drove steam locomotives harder and harder. They made them bigger, they made them more expensive, they went to steam turbines, they did everything they could to prevent the takeover of diesel engines. And there was a sea change in the industry, and the successful companies in diesel engines were not the successful companies in steam engines. It's because it was a fundamental change in how business worked. We are facing that. We are going to see a change in the industry. I call it Foundry 2.0. I'll say more about it later. Advanced packaging allows us to do lower volumes at much more cost-efficient price points. It's better size, weight, and power, better performance, better cost. It really gives us everything that we have come to expect from Moore's law, and will and really need to keep the microelectronics revolution going. So what is advanced packaging? It comes in many different forms. It's been around for years. It's just that it's been very subtle. Xilinx was probably the first mass volume product that we all at least heard about. However, everyone in the room here has a 3D integrated circuit, probably in their pocket. All cell phone cameras are 3D integrated. There are 100,000 300 millimeter wafers built every month using 3D integration. They're all in Asia. Sony, Samsung, and Tsinghua do almost all of that. The next entry was really using interposers in the HBM memory stacks driven by GPUs, because it did something that couldn't be done any other way. At the end of the day, what 3D integration resolves is it reduces wire. Wire is the problem. It is all the delay, and it is most of the power. If you can reduce wire, and 3D does that better than anything else, you win. And further node shrinks really does not give us that. So what are the elements of it, the building blocks? First and foremost, my opinion, it's bonding technology. We use covalent hybrid bonding, the Xperi technologies, Ziptronics. I actually own the original Ziptronics fab. That's where we build our stuff. Nhanced has delivered to customers 20-layer stacks. Don't build a lot of them, but we build some. We can do bonding with a wide variety of materials. Today, we bond gallium antinomide, gallium arsenide, gallium nitride, silicon carbide, lithium niobate, indium phosphide, many, many different materials. More than half of what we build is truly heterogeneous integration. Most of it is at 4-inch, a little bit is at 8 now. Seem to be kind of skipping over 6. What bonding technology fundamentally allows us to do, in addition to reducing wire length, we can change millimeters to microns. A 3D solution reduces wire length by 90–95%. 2.5D is not bad. It probably gives us 80%, 75%. So it's a great first step, but 3D is the ultimate solution. Bonding technology, because we can intermix all of these other materials, it leads to chiplets. That's another story. But we always can have the highest performance. The Johnson figures of merit, and I learned that in the Dahi program. We can get 10x, 100x, 1,000x performance improvement. I'll give you an example. Artificial intelligence is moving to photonics. It's because a lens does a matrix multiply. It is 1,000 times more power efficient than CMOS will ever be. But in order to do it, you need to do heterogeneous integration, and it really needs to be bonded because of the density. So how do we do this little miracle? DBI is the trade name that Xperi uses, direct bonded interconnect. So it actually is pretty straightforward. In our fab, for the most part, the first thing we do is we add a layer of copper or nickel interconnect on top of the wafers. We polish it atomically smooth with CMP, do an activation. It can be chemical or plasma. And then at room temperature, you can bring the wafers into contact and they instantaneously bond. You get a room temperature van der Waals bond. The good news is that they stick and they don't fall apart. The better news is that we can look at it and see how good the bond was. And if it's not good, we can take them back apart, clean up the wafers, do a little repolish, put them back together again. That bond is not permanent until we do the anneal. So with this technology, most of what we build in our factory today is 3 to 5 micron pitch interconnect. So we have millions of interconnect. You can have bandwidth, which is in petabit per second range. Just a data point, the capacitance you get is about the equivalent of an 8x drive fan out if you're a chip designer, and that's inclusive of a TSV. Most of the layers are very thin. The pitch at which we can bond experimentally, we've delivered to a customer a 0.8 micron pitch. Our line is rated to 2.44 microns. And that's at wafer scale or at die to wafer. Literally, we use the same bonder for both. There's no difference. Another element of advanced packaging. We need circuit cards, interposers. Interposer technology is still relatively immature. Most of the world is being supplied with silicon interposers that use the last 3-layer process from a 65 nanometer node. We do build interposers in our fab. Silicon, borosilicate, infused silica, which I'll shout out to Mosaic. I get the glass interposers from them. They have a great handling system for what it's worth. That technology is the future path forward. We are going to move from today's SoCs that are monolithic to a chiplet-based world with silicon and glass interposers. And eventually, there's a dotted line trail here to panel manufacturing. As I mentioned earlier, wiring is the problem. I lump wiring into the area of additive manufacturing. The path forward, the new technology, the next generation of semiconductors is advanced packaging married to additive manufacturing. The advanced packaging with the ability to add special materials, more metal interconnects, will drive the ability to have much higher performance systems. It is bringing all of those different devices together intimately with very short interconnect that drives the future of microelectronics, and doing it much more cost effectively than a 1 nanometer process that does everything. And of course, as we bring in the additive manufacturing, it really enables that. It's all of those other things. And I can tell you, at some point or another, we have done every one of those except the battery. So we build antennas. I have a program today which will build antennas on glass substrates. We certainly have done all sorts of things with lasers and photodetectors for transceivers. We have thermal solutions with liquid cooling that are bonded into stacks. The ability to mix these processes, do additive manufacturing, combine them with the advanced packaging technologies is the future of microelectronics. Another facet of this is chiplets. Chiplets is revolutionizing our industry. And if all you have to do is look at what Intel and AMD are doing, what Xilinx and Altera have been doing for years already. Marvell does it. Building chiplets allows the market, allows those entities in the market to target niche markets, do it much more effectively, and do it quickly. The problem that companies face today is if every chip development is 100 million plus, how many markets can you address? If you go down the road with chiplets, you can address markets that are now measured in thousands or tens of thousands of parts. It doesn't have to be millions and tens of millions. Advanced packaging is fundamentally enabling for our industry. You can do other very unique things. And I'll point out here, there's MEMS devices, certainly. We work with IIC. That bowl up on the right-hand side, that has 46 chips in it. It's put together by Quilt Packaging. And those devices are 3D devices also. So ultimately, when that's delivered, that's an IR sensor. It has heterogeneous integration, an interposer. It's stacked with CMOS devices and then quilt packaged together. The interconnects are on the edges. And the final deliverable, I think, is going to be 70 some tiles. So that exists today. That's not a cartoon. Microfluidics and cooling. Everybody brings up, it was brought up this morning, as we start stacking these things, they get a little toasty. We're probably going to have to do in-stack cooling. We've done some of that. We had a government program some years ago. We built these two-phase liquid cooling blocks and put TSVs through them so we could distribute them in stacks. We moved 2,200 watts in a stack, far beyond what you could do with any kind of two-dimensional cooling. Microfluidics, they're necessary for bio devices. They're necessary for some sensors. This is going to drive that next phase of bringing components together. How do we take the system today and continue to shrink it further? If I go back to my first statement, it's the wire, guys. That's the limiting factor. How do we limit the wire? We got to bring the systems down to that, chip level, 3D and very dense 2.5D advanced packaging technologies. Other things we can do. Photonics. We're all aware that photonics is being done, and I said I would point it out to you earlier. So on the far right there, we just delivered that. That's a IC that is die bonded to a PIC from AIM on a custom substrate over there. We actually just delivered that to our partner. That's a DOE program. We are starting to do some quantum work. Quantum is additive manufacturing, and it requires, at least eventually will require 2.5D assembly. In order to make it effective, in order to get high enough density to build the quantum computer that can solve the first problem of interest, which is nitrogen fixation, we're going to have to use 2.5 and 3D technologies. It's not a choice. It is the only possible way to build those machines. I already mentioned for artificial intelligence, to do much more power effective artificial intelligence in the optical domain. We're building today copper and waveguide interconnect simultaneously on interposers, bonding components to it, so you can build this electrical optical system with heterogeneous materials in order to achieve the next generation of artificial intelligence. So those accelerator technologies that were pointed out this morning, in order to make those work, they are driving advanced packaging as the solution. Other things we can get out of it. Size reduction. That's a root of trust on the left-hand side. On the right is a root of trust that we're building. It's a government program. We do a lot of those, not exclusively, but we do a lot. We have a 75% reduction in size, weight, and power. Does exactly the same function. Well, why is that important? It's because as we make cars more autonomous, more intelligent, we want to reduce the weight. It's got to get smaller. If our military systems, retrofitting those, there's a particular program I have in mind. They need to retrofit the guidance system of a device. We're now moving into an era of hypersonic weapons. So you need a lot more intelligence and a lot more capability in something that has to be the same size, weight, and power that it was when the system was originally built 30 years ago. The only way to do that in a niche, low volume business, which is the business of the US government, is with advanced packaging. One of the other areas that we're seeing a lot of pull through is in edge devices, especially sensors. You want to integrate the sensor. You now want to process at the sensor. Think of your cell phone camera, which now has a 50 megapixel camera in it. That is the direction that we're tending to go with a lot of the sensors. The problem is the backhaul. In order to really effectively use those sensors, we're needing to process at the sensor. We have a lot of data. Data movement costs power. And beyond power costs real money, because if you need more cable, you need better transceivers, you need photonic interfaces, fiber optic, all of those things raise price. But if you can do the processing, heterogeneous integration at the sensor, you save power, you save time. Time of flight is a problem. Jet engine controllers are mounted on the jet engine. They have been for decades. It's a terrible environment. It's hot. It sits on the tarmac. These things can have to survive 150-degree operation for extended periods of time. Why would you do that? Because time of flight requires it. Okay. So the future that we see is a finishing fab. We see the industry changing. The quintessential foundries today, they're not going away. I'm not predicting the end of TSMC or Intel or any other company, but I think they're going to manufacture chiplet feedstock to Foundry 2.0. Foundry 2.0 will be about advanced packaging and additive manufacturing. It is well geared, well suited to high mix, low to medium volume production. At least that's what we're targeting it. Not saying you can't do high volume. I already said all of our cell phones and cameras are done. That's high volume production. Works great. But how do we save our own industry? If our industry continues to focus on only the very largest companies, you know, we're going to end up in the world of threes. There will be 3 manufacturers of all semiconductors and probably 3 manufacturers of all electronics. It kills, stifles innovation. In order to innovate, we have to give a mechanism back to the industry to have startups that don't all have to be unicorns and raise $1 billion. Advanced packaging will get us there. The Foundry 2.0 is what we think. So we're building a new fab. We have a fab in Indiana. So this is my brief commercial. We're building a new fab in Indiana, one of those flyover states, meant specifically to do advanced packaging. I talked with the site developer yesterday. We should have the shovel in the ground in November now. You'll notice we're planning a laminate facility. Now, I'm not saying we're running it. I have a partner in that area of the business. But the reason it's attached to the fab is because advanced laminates require semiconductor processes. And as a stepping stone to glass panels, to very fine line organics, you need lithography, you need CMP, you may need etch processes that are semiconductor-like. So the need to build laminates next door to a real semiconductor plant, we think is required in the future. So, and as it says, this is about 50 times the capacity of our existing fab. And the slides will be online. We support all sorts of processes, a wide variety of different types of advanced packaging. I'll give a shout out to Acceloprint in the back. We like their stuff. The IIC quilting. We do wafer reconstitution. We've done wafer reconstitution, putting die to wafer. The die were heterogeneous, replanarize it and stack another layer on it. These are all low volume. Nhanced is a small fab today, although we're doubling in size now every year. So I'll summarize. The road ahead. We're at a sea change in the industry. We're going to see a significant shift. We talked about workforce development. It's very important. But I'll tell you, it's going to be very challenging in a much different way that we may not be seeing. The automation is not the problem. I mentioned this to Jan. The problem is the engineers. Advanced packaging requires probably 4 times the number of engineers as standard silicon development. There are many more alternatives. There's much more development, and especially if we move into an era of low to medium volume customization, which is enabled by the cost structure of the technology and the resulting performance that you get from it. So workforce development is going to be a significant key factor. We need more engineers, a lot more. Advanced packaging is driven by economics. It's not driven just because it's neat. It is neat, but really what has allowed it to start to become the standard in the industry, the path forward, it's because the economics drive it. And we strongly believe in the need to onshore, and of course we're active in doing that. That probably goes without saying to this crowd. That's my last slide. I think I left sufficient time for any questions. Thank you very much.
Additive manufacturing, equipment, materials, even for low volume equipment and materials for manufacturing, from design all the way to the product.
It's a new area that I'll give you. And actually, I've talked with AMAT and TEL about a need for changing the semiconductor equipment to better address a high mix, low volume environment. You go to any of them today, and the first thing I want to tell you is how many wafers per hour they can do in that machine. That's fantastic. How long does it take me to change a recipe? How many test wafers do I need to run after I change the recipe? In the next year, a semiconductor, that's an important thing. It's not just how do I build something that is in millions and millions. It is how do I do it with a minimum number of wafers and the most number of changeovers per day. So that's one answer on the equipment side. The materials, there's many different materials that we're looking at. If you just look at something simple like the different memory technologies, requires some specialized equipment for like MRAM, even for our RERAM. ALD, I think it's an expensive process, but in low volume, it's much more cost effective because the yield can be higher. That's one of the things when you start doing low volume manufacturing, there may be more cost effective ways to do things that don't make sense at high volume. Low volume isn't you just take a high volume fab and shrink it. Low volume is specifically engineered, laid out to do low volume production. Because if you just take that big factory and shrink it, you hear the horror stories. Oh, you know, it took so long, cost so much, it doesn't make sense. And they're right. What else did you ask, Bill? Design. We need much better. The design tools have come a long way. They have a long way to go to be able to do more of the simulation, and there are now advanced packaging development kits that are coming out. One of the first experiences I had with packaging, probably 20, 25 years ago, we built a substrate. We designed it ourselves. We asked for design rules. They kind of gave us design rules. We sent it to them. And they look at us. We can't possibly manufacture this. I'm a chip designer. You give me a set of design rules, I designed the design rules. The guys building the substrate said, it's not manufactured. I said, why? We followed the design rules. Yes, but you did it all over. The packaging guys, the substrate guys for years have lived in an environment where they really aren't hard rules. They're softer. Chip guys, because the designs have always been so large. We have hard and fast rules. If I say it's 2 microns, it's 2 microns, and every wire can be 2 microns. The PCB guys have been in a different world. And it's not just because they use Gerbers and not GDS. So I think that we have growing pains there. It's the figuring out the simulation yield, it's the thermal solutions, and it's figuring out the flows to assemble these things. As we bring together different technologies, it's going to be important that the design rule systems, the checkers, the validation tools, the simulation modeling tools grow up to support the capabilities we have in advanced packaging.
Thank you. So I think time's for the next speaker. Thank you very much, Bob. So our next speaker is Hemanth. Well, I'm sorry, I did not pronounce it correctly. So Dr. Hemanth leads the computational modeling team in the advanced packaging group in AMD. He is responsible for thermal, mechanics, and multi-physics modeling capabilities to enable new packaging architecture. Before joining AMD, he spent 12 years at Intel working as a technologist in packaging. He has a PhD in mechanical engineering from Purdue University and bachelor's in mechanical engineering at our Indian Institute of Technology in Madras. He authored over 20 publications and 15 patents in the field.
Thank you, Bill. Good morning, everyone. Today I'm going to talk about AMD's advanced packaging and enabling the heterogeneous integration through the chiplet architectures. So if you look at the growth in the connected devices in the last 40 years, we had this PC and the web browser era, followed by the smartphone and apps era, and now we are moving into the HPC era, which is largely driven by the growth in the data center and AI, whether it's 5G or adaptable intelligent systems like or robotaxis or edge compute. It's basically leading to explosion of the number of connected devices. And what this means overall is there is this relentless demand for more compute. And here's a chart kind of showing you what is the growth in the amount of compute in the HPC space over the last 30 years or so. And you can see that the trend kind of shows that it grows about 2x every 1.2 years. So this is actually growing faster than that of Moore's law. So what it also implies is the innovation that has happened in this space was more than just the raw silicon innovation happening in the Moore's law. And as Mukesh highlighted this morning, the compute is actually increasing even further. It's doubling every few months now. So because of this, the new applications that we are finding, whether it's a climate change or machine learning or finding some drug delivery systems. Let's take a step back and look at where's the status of the technology to meet this demand. And if we've talked about like the slowing of Moore's law, several speakers have addressed this morning, and you can clearly see it's actually slowing down. And coupled with that, as Bob mentioned earlier, is like we had this increase in the wafer cost, and the cost of per transistor is actually going up. Another aspect to consider is the different scaling factors for the various silicon. So if you have the logic has a good benefit with the scaling of the shrinking of the node, but SRAM and analog, they kind of take a different path. And when you put this all together in an SoC, you kind of see that the SoC scaling tends to plateau out after a few years. So where this all leads us is, we need to look at a different way of architecting our packaging, and we have a huge compute demand, as we looked at earlier. There are a lot of barriers to our traditional scaling following Moore's law, and we have new applications like with specific accelerators, where we're addressing either machine learning or like doing edge compute kind of problems. So what is needed is we need to look at something more on the modular design supported by advanced packaging. And in this particular case, several speakers have talked about this earlier too, using chiplets, right? And I'm going to delve deep into the next few slides on chiplets. So this is a high-level approach to chiplets here. If you want to take a very basic view, let's start with a full reticle die in a wafer. And if you assume a certain number of defects within the wafer, you end up with a limited number of functional SOCs. And let's just say you split the same silicon into 4 chiplets. And with assuming the same number of defects, you have increased the yield of the wafer now. So the yield starts to work in your favor, and you can make many more functional SOCs than you were able to make before. So this is kind of giving you the yield benefit of going down the path of chiplets. And we are able to mix and match these different silicon to give high performance processes as well. So looking at the modular architecture goals, right? I've mentioned about you can mix and match these various chiplets depending on the speed and the market requirements for the particular segment. And it could be, different chiplets, whether it's a CPU, GPU, or a different functionality to meet the product demand. So I've shown this architecture before. AMD led the way with MCM back in 2019 by using chiplets, CCD chiplets on the periphery and the IOD chiplet at the center. So this is one particular instantiation of the packaging architecture using chiplets. These are some more InfoR, InfoPop, and Focus. These are RDL-based architectures where we connect the chiplets using RDL. And there are 2.5D architectures, which could be EMIB, co-EMIB from Intel, or InfoL or a CoWoS-L architectures from TSMC, and also Interposer. Moving on to 3D, so there's Foveros from Intel, and wafer-on-wafer stacking, and using microbump-based stacking, which is used in the memory industry. So where this all leads us is basically you can see that this is very specific to the particular architecture being discussed. So there's not like a one-size-fits-all. We have to look at what are the product performance needs, and then accordingly decide on the architecture. Let's look at some of the key factors influencing this decision for making an architecture choice, right? So we've talked about the 2D architecture, which is the 2D MCM. It's basically a very simple architecture. It functions really great. It's a low-cost architecture, but the bandwidth requirements in this particular case are sufficient to meet the connectivity between the compute CCD chiplets that you see on the periphery and the IOD at the center, right? And one of the ways to quantify this is linear interconnect density, or an areal interconnect density, which is number of wires per millimeter square. And on the x-axis is the performance. So you see this, the 2D MCM is kind of at the bottom, kind of giving you an idea of where it would land. And if you take a step further, look at, you want to increase the bandwidth, for example, It could be a high bandwidth memory in connection with a compute engine. It requires a lot more interconnect because we're talking about terabytes of data. So that is where the silicon interposer architecture takes a very good role. And here you can see the interconnect density offering for the case of a 2.5D architecture, which is a significant leap over the 2D. Another offering in that space is also a EFP architecture, which we are calling it as elevated fan-out bridge. And I'll talk about it a little bit in detail in the next few slides, which gives you a cost advantage over the silicon interposer and gives you similar performance. And the holy grail is going down the path of 3D chiplets, right? How do you stack chips on top of each other and achieve the highest performance? And we've heard this from Shin in the morning, like Z is greater than X and Y, right? So anything that you can do to stack the chips in vertically, that gives you the best performance. So in this particular case, we are talking about AMD V-cache architecture, where stacking the SRAM memory on top of the 32 MB L2 cache gives you a significant leap in performance of the product, offering almost like a 15%, which is like a generation improvement in performance. So let's look at this, the 2.5D architecture that I mentioned in the previous slide. So on the left is showing the industry instantiation of like a 2.5D, where a bridge die is embedded within the substrate, and the two dies are interconnected on the substrate. Now, in this particular case, you would need the substrate to have a cavity to accommodate this bridge die, and it would need very high tolerance of the die placement as well as the chip attach tools in order to achieve this fine pitch. So it offers a better interconnect compared to that of a silicon interposer, and it has a better electrical because of the lower parasitic resistance, because we're eliminating the TSVs. Now on the right is what we introduced in MI200, which is called as elevated fan, which we're calling as elevated fan-out bridge, where the bridge is now embedded as part of this molded complex. It is surrounded by these copper pillars that you see on the right? So, and in this particular case, this is a much low-cost architecture compared to that of the instantiation that you see in EMIB, where we reduce the cost of the substrate because we've eliminated any need for drilling the cavities within the substrate. And we can use a standard flip chip process as opposed to using a higher cost requiring complexity in terms of the bumping and assembly processes. And also, this particular die complex can be lithographically defined, so it is a lot more scalable in building larger die complexes. And this is the product that we've introduced, late last year. This is the MI200 employing this elevated fan-out bridge architecture, where we've connected this compute engines, the high bandwidth memory with these localized bridges that are there in this molded complex, and giving you a significant boost in the performance, and while offering this technology at a much lower cost. So moving on, another architecture that I showed in the previous slide is the AMD 3D V-cache. Again, the motivation for this is, as highlighted by many speakers earlier, is how do we achieve this high interconnect density in the Z direction? And in this particular case, I'm pointing out to the L3 cache, kind of giving you a significant IPC uplift as we increase the size of L3. And this has been the industry standard. If you compare many processes over the last few decades, you can see that the cache memory has been increasing. But what we've been observing more lately is that the amount of cache has started to plateau out for the reasons that we talked about earlier, because of the slowing down of the Moore's law, and we cannot pack them more anymore. And Coupled with that is the SRAM doesn't scale as effectively as that of the logic. So you're not able to pack as many as that of the logic. So it requires a different way of doing the architecture. And hence the case for 3D stacking. So in this particular case, we're showing you the AMD 3D V-cache architecture where we stacked SRAM silicon on top of the what we're calling as a CCD, which has, and I'll talk about the details of this CCD die, which offers a significant boost in terms of the performance, where a 64 MB cache memory is stacked on top of a 32 MB cache, providing like a huge improvement in performance. It reduces the memory latency because it is directly connected vertically and through the TSVs. And you're able to fit in a lot more transistors for the given footprint in the package. So the components of this particular architecture are the bottom die, which is the CCD. This is made of a TSMC N7, where we have 8 cores in the die, which you're calling as CCX, a core complex, and also has a 32 MB cache memory at the center, as you can see. These CCD connects through the L3 cache using the signal TSV arrays that you see in the center in the blue boxes. The other component is the L3D cache. So that is the top die, which is shown in the red here. So the top die communicates with the bottom die with the TSVs, and you see that the AMD 3D V-cache technology extends this to overall to a 96 MB L3 cache. So how do we bring this all together? He is using this hybrid bonding. So in this case, the bottom die is the CCD die, which is thinned down to reveal the TSVs, and it is connected to the top die using BPM, which is the bond pad metal, as you see in the red. The bond pad metal is connected to the metal 13 using the BPV, which is the bond pad via, as you can see in the picture. And the current pitch is a 9 micron minimum TSV pitch, and this is giving you basically the 96 MB cache offering. And the CCDs that you see on the east and west in this particular image, they have a structural silicon that is oxide bonded on top of the CCDs to allow for the thermal dissipation. So how does this compare to the industry standard, right? We've looked at some of the industry offerings in the previous page. A lot of them are microbump-based architectures, and typically in the range of a 50 to 36 micron pitch so far, and maybe there is a little bit more room in terms of scaling that pitch to perhaps 25 or so. But regardless, you're limited by the microbump. And compared to that of what we are offering in this hybrid bond, which is a 9 micron pitch, what this leads us to is a huge improvement in the interconnect efficiency and the interconnect density compared to that of a microbump, and while offering better parasitics in terms of the TSV inductance and the capacitance compared to that of a microbump. So what this leads us to is almost like a 15% improvement in terms of performance over a monolithic die, which is basically considered like almost like a generational improvement in performance that gives us a huge uplift over our competition. And what's the future of 3D stacking? I think we've just started this journey on the 3D space, with showing you the L3 SRAM stacking. But as we shrink the TSV pitch from what is today at 9 micron to possibly a micron, 1 micron or less, it opens up possibilities of doing a lot more architectures. So it could be we're looking at like a CPU on a CPU stacking or a DRAM on CPU, to a core on uncore stacking, or an IP on IP, or an IP folding. Could be a macro on macro stacking, or even like you can split the IP and fold it, or even more fancy, looking at even slicing at the circuit level. So all in all, I think we just scratched the surface of this 3D stacking, and this will lead us to a lot more complex designs in the future, and offering the compute, high compute that is needed in the HPC space. So in summary, we've talked about how the compute is increasing significantly than what has been the case in the past, and what we are doing in terms of this chipletization to meet the demand of this high performance compute era space that we are in. And especially the improvements are coming from the advanced packaging, whether it's hybrid bonding or the 2.5D architectures, allowing for the high bandwidth communication between the chiplets. So yeah, that's all I had. Thank you. I think Shin presented this morning about how we can do a Victron stacking. He was showing almost like a 4 or 5 year stacking, what we can achieve while still meeting the thermal demand that you mentioned, right? So we are together. We are AMD. Yes, sir.
There's different ways to partition the SoC. And so I'm assuming there may be 3 or 4 different ways to do it. When you started your design, how do one select the best possible chiplet design for market?
Yeah.
You are the simulation person, so I'm thinking about you're thinking, I'm thinking about this thing all upon your lap and saying, how do I do it?
It comes down to, I mean, we've looked at the various 3D packaging architectures, and it comes down to PPAC, right? Performance and area, cost, all those assessments that we have to do, and the availability of the technology to meet it. So, for example, the 2.5D that we showed is a huge cost improvement over the industry offering. Same thing with the 3D as well, right? Depending on what chiplets that you want to stack, you may have to pick a different technology. We cannot stack today like a high bandwidth memory on a CCD, for example, or a compute engine, maybe in the future. So depending on the availability of the technology and as well as the performance needs. To figure out. Maybe. Not yet from my end, at least.
Alignment. Over 27 years, Alan has worked at International. He was at NCNC, and he is currently at Skywaters. He has been active member of IEEE Electronics National Society since 2005, member of the ECPC Organization Committee, and serving a technical committee. He is currently served as membership committee. So if you'd like to join the Electronic National Society, please see Alan.
Thank you, Bill. While Vince is pulling up my slides, it occurred to me over the last 5 or 6 years that whoever is the last person presenting in a session is inevitably going to repeat a number of the points that have been made by the previous speakers. So I'll appreciate your forbearance because you're going to see some of this that you've already seen before. All right, thank you, Benson. Okay, so I've pulled these directly out of the headlines that have been put up over the last several months. I don't think any of these will come as a surprise to you. Obviously, I've even picked out here some of the larger companies that you've seen in the industry. Everybody is building a new fab, not the least of which is my own company, Skywater Technology, who announced that we're building a $1.8 billion facility in Indiana that's going to be butted right up against Purdue University and is going to be focusing on legacy technologies. We all know this part. Okay, this is one of the very positive outcomes of the CHIPS bill. And we also know the story with this information. So the U.S. contribution to global semiconductor manufacturing capacity has fallen to about 12%. Dr. Gale showed some of these statistics earlier. We all know that foreign governments have invested heavily in supporting the growth of the semiconductor industry in their countries. And so as a result, much of the manufacturing capacity globally now resides in Asia. And that includes most of the leading edge technologies in CMOS device fabrication, as well as all of the advanced packaging technology capabilities for high volume. And the COVID pandemic has exposed a lot of the vulnerabilities of that supply chain, but there's been concern about this question for a lot longer than the last 2 years, particularly over the ability for the U.S. to maintain the security and technological superiority of some of its electronic systems. We all know that this is a ubiquitous need for a stable and secure supply chain. I've just picked out some of the top industries here, markets, if you will. We all know that there's security needed in automotive. Banking is a very obvious area where electronic security needs to take place. Consumer electronics, of course, are a big thing. Industrial, utilities, cloud and big data, all of these are industries that demand a stable and secure supply chain for their electronic solutions. There are also defense and national security needs as well that are pretty well known. I took this slide from something from February of 2019, where Dr. Moldavan was presenting on a lot of the dependency for next generation systems that were going to require these microelectronic technology solutions. You can see a number of these in cyber and quantum have already been discussed today. Mesh networks that are secure and stable, artificial intelligence and autonomy are well known in both areas. Directed energy and space and hypersonics. And our continued reliance on non-US microelectronics creates supply chain risks and it creates security risks. And of course, we all know that the volume requirements of this market are substantially lower than you would get from the consumer market. So there becomes this natural tension of whether or not we're going to be able to support the manufacturing requirements that we need for stable onshore needs at a cost-effective price point. Adding to that, establishing security requirements within existing commercial providers is often not feasible to do. It's very hard for us to go into foreign countries and ask them to open their doors to us and let us look at all of their systems and vet that all of their microelectronics components that they're providing to us are secure. So how does this then focus on the packaging industry that we're so focused on today? You've seen this before, but the current estimates put the U.S. contribution to global semiconductor packaging at 2 to 3%, so even lower than what we're doing in advanced CMOS nodes. None of the major OSAT companies have manufacturing operations here in the U.S., though most have engineering or sales or management operations here. But there are several companies who have prototyped low volume capabilities in advanced packaging and heterogeneous integration technologies that have been supported both by government programs and by commercial businesses. And this has been a situation that's existed for 25 years or so, certainly as long as I've been in the industry. While a majority of that 50 billion plus for the CHIP program is going to fund front-end device manufacturing capabilities being developed here in the United States, a significant effort is going to be focused on development of the advanced packaging and heterogeneous integration manufacturing capabilities that are going to be crucial. This doesn't need to be reiterated. You've heard it. I think Bob always speaks about this very eloquently because he really puts the holistic system perspective into focus, talking about the fact that this is not just a way to do things. In many instances, it's the only way to do things. So at the risk of then repeating what Dr. Gale has already given this morning, the two main program initiatives that are going to be established on the CHIP program are the NSTC, which is a public-private consortium that's establishing R&D and prototyping for advanced semiconductor technologies, and the National Advanced Packaging Manufacturing Program that's going to have a directive of establishing up to 3 manufacturing USA institutes. In total, this is $2 billion and $2.5 billion respectively for the first year, and an additional $6 billion that's going to be broken down over the subsequent 4 years. So there's a substantial amount of economic investment that's being put forth by the government to support this initiative. And there has been a tremendous amount of preparatory activity that's been taking place over the past year to prepare and plan for this effort. Notably, the Department of Commerce noted that they received over 200 responses to a request on how these funds would be best used to establish those manufacturing capabilities. I'm sure a lot of people sitting in this room work for companies that submitted their own responses. And then there are other organizations, the ASIC Coalition being one of them, that have been pulling together companies and universities and national labs together to create long-term plans from a very high level to help provide solutions and paths that can be ready to provide to the government when those calls are ready to be issued. Now, establishing a secure ecosystem for an advanced packaging goes far beyond just putting together fabs that are going to be putting together silicon. There are a lot of elements to this initiative that are going to have to be taken on as well. And I've tried to lay out a lot of the main points here. Starting with design, you need EDA software, you need multi-physics modeling, that's no surprise. The substrate side of this has been heavily discussed already today. You need PCB, you need high density laminates. Ceramic is probably going to continue to play a part in this to some degree. I group then now the interposer technology, silicon and glass, into the substrates as well because they're integration platforms. What do we do about physical interconnect? Well, you've got wafer level CSP, you've got bumping, you've got copper pillar, direct and hybrid bonding, all of these technologies that are now physically interconnecting different pieces of silicon. You have back-end processes. All of these devices are not being assembled on full thickness silicon for the most part. So you need wafer thinning. You need the ability to be able to do dicing and singulation and handling of all of those thin pieces of silicon. You need now the ability to do temporary bond and debond while you're handling these thin pieces of silicon. On the assembly side of things, you've got flip chip, you've got thermocompression bonding, you've got direct hybrid bonding, again, as back from the physical interconnect side of things. You've got fan-out wafer level packaging. You even got the need to continue to do SMT technology. So all of those still have to be comprehended in this. Testing is a huge part of the equation. How are we going to continue to do wafer level or module level testing when we're now disaggregating all of the components that used to work all together and now having to test them as separate functional blocks? The reliability aspects of these go without saying. both for commercial applications and for high reliability applications, space and defense, for example. And you still need to be able to do some level of COTS upstream, taking commercial off-the-shelf parts and being able to vet them to a higher reliability standard than they were originally intended so that they can be employed without the need of creating a brand new system is still a very important application. And then you have materials, you need equipment, you need security protocols that go down over all of these for some applications. And most notably, as has already been discussed a lot today, you need a workforce that can implement all of these different parts of this ecosystem and make it sustainable here in the US. So this is where I'm going to enter in with a little bit of information about my company, Skywater Technology. It is the first US-based pure play service provider for silicon interposer, fan-out wafer level packaging, and hybrid bonding technologies. It is utilizing unique silicon process capabilities being established right now to support 2.5D and 3D microsystems for commercial and government customers. Our intention is to develop a pure play foundry capability to support all of these heterogeneous integration technologies. It's ITAR registered with workspaces and fab capabilities to support high security. And it really is a true public-private partnership. It is an organization that is comprised of agreements between Osceola County and Florida, a not-for-profit organization called Bridge, and Skywater as a publicly traded company to really utilize the strengths of those three organizations in implementing solutions, developing technology programs, and ultimately being able to bring those technologies to a wider group of users. Of the three technologies that are our platform technologies, I wanted to start with the silicon interposer development program that we're working on right now. This is developed on a license that we took from IMEC. So if you're familiar with IMEC's interposer technology, then there's going to be a lot of elements here that will also be familiar to you. It's currently being supported by an industrial base analysis and sustainment program. So the implementation of that started a few years ago. Skywater took over the operational and engineering aspects of this program in the middle of last year. And it's a 4-phase program right now that essentially begins with the establishment of a silicon bridge interposer capability, which is a damascene process capability, is now in phase 2, where we're implementing our TSV process and integrating that with the front-end damascene processing. There's a phase 3 that'll start later this year, which further increases the number of routing layers on the front and the back side of this technology. And then further out, covered up by the screen here, is an RF version of this interposer that will incorporate both damascene routing capabilities and polymer dielectric RDL technologies. So less concern there about density, much more concern there about the capability for RF integration. This technology is being stood up, and there are programs that are immediately following it. In fact, one of them is about to start now that are functional demonstrator programs that utilize this technology. So the basic process capabilities that are being established in this IBAS program are being closely followed with functional real-world demonstrators. A couple of pictures here of the TSV process that's been developed here. You know, I think you've seen these a million times, but I always like to show cross sections of real things as opposed to PowerPoint pictures to show that they really do exist. And then a little bit of a summary about that technology and the roadmap. So TSV size that we're going to be focusing on and standardizing around is 10 by 100 microns. That's pretty standard. I don't think that's going to surprise very many people. There will be capability to expand around those dimensions for different applications. Up to topside metallization up to 4 layers, backside RDL and solder bump structures. And we have daisy chain and functional hardware designs in work right now. There's a design manual for this technology that's in beta that we can distribute under NDA. And the roadmap for that technology to have phase 1 qualified, that's completed. Phase 2 is expected to be done later this year, with phase 3 following it in first quarter of next year. So by the time we get to middle of 2023, we anticipate having a full process design kit that we can provide and scaled manufacturing capabilities to be able to support initial customer information or inquiries. There's also the interest in taking this technology a step further. We've talked about vertical stacking, and the fact is that devices that are going to be vertically stacked are typically going to need to have TSVs incorporated into them as well. That is not always a possibility to get from a foundry, though the capability is expanding. One of the things that we've been approached about and get a lot of inquiries about is the insertion of TSVs into CMOS devices that are already finished. So that's something that I have some previous experience with. It's something that I think is going to be an interest for a lot of customers going forward who don't want to redesign silicon, don't want to go out and refabricate silicon, but have the ability to incorporate a TSV that's been built into their device after the CMOS is finished. The second one of our platform technologies is in fan-out wafer level packaging. I think a lot of people are aware of this technology and very aware of the fact that there are a few main players in this industry right now. Skywater recently announced that we were partnering with DECA to implement this technology into our Florida facility. Not only does it provide a pathway to enabling IO footprint extension beyond the silicon device area, but it also provides an opportunity to integrate multiple devices into a single package. The DECA technology is a chips first, chips up fan out technology. There are ways that you could do this a little bit differently. There are certainly a lot of different architectures right now that are comprehended around different fan out based technologies that incorporate bridges, that incorporate multiple layers of devices that are being integrated at different points in the processes. So this is something that we're also looking at as well going forward, particularly beyond what DECA's volume manufacturing capability is today, a process that's called M series that's been well established in a couple of foundries in Asia today. Looking forward, we're going to be working with DECA to help them establish what they call their M series Gen 2 technology, which will incorporate now smaller RDL dimensions, more routing layers, the ability to include devices with smaller IO pitches, and also to put those devices closer together within the package. You can see a few of the different applications here. The timeline here is a little bit stretched now, but the Gen 1 technology, which has been involved in high volume manufacturing now for some time, is doing a lot of its volume work in PMICs and IoT devices and codec types of devices. Gen 1.5 now has started to incorporate some package on package types of approaches, fan out SoC, for example. All of that can still be done with existing lithography and AOI equipment. It still allows you to push the envelope a little bit in terms of integration without the need for additional equipment sets. The Gen 2 capability will have to push the equipment further than what is established now in high volume manufacturing. So it's going to need not only the new equipment, but it's also going to need further material optimization. It's going to need to have new design rules put around it. There's also the incorporation of things like through mold via structures that are now going to be different lithographic processes, different plating processes. And all of those are intended to be established at Skywater as we bring this technology in and continue to develop it. So a little bit on the roadmap for that. The M series process today, if you're not familiar with this, supports 2 RDL layers and a minimum of 10 micron line space, 55 micron die bond pad pitch in the package. So the devices themselves that are integrated have 55 micron pitch, 100 micron die spacing. The Gen 2 targets will push that number of RDL layers to 4. It'll also push the dimensions down to 2 microns. So again, a tremendous increase in the amount of interconnectivity that's possible in the package. 20 micron die bond pad pitch now instead of 55. So you're looking at a much higher interconnect density on the devices themselves and a reduction in the die spacing. So we're cutting down the interconnect length between the devices as well. We are working now on demo test vehicles to bring this technology in-house. We are also in the process of identifying and getting equipment in place. And if you know anything about equipment today, the lead times for these things are going to take some time. So we're going to be working in some outsourced partners in the near term while we bring our own equipment set in and have this technology installed. But even with that outsourced capability, we're expecting in early 23 to be able to begin to start looking at some initial customer capabilities and engagements. And the final technology is hybrid bonding. You heard Bob talk about this extensively. His group's been doing this for 25 years now. And his is a very unique implementation of this technology because most of the people who establish hybrid wafer bonding capabilities or take a license from Xperi are doing it to enable their own devices or their own architectures. And Skywaters' approach is going to be somewhat similar to that which Nhanced is doing, which is to offer this technology as a service to parties who want to come in and take advantage of it. That does mean that there's a lot of customization in the processing and there's a lot of differentiation between devices and how you're going to apply this technology. And so we are in the process now of doing that tech transfer with Xperi. Our license was signed in May. And not only is there the hybrid bonding that has an electrical interconnect component to it, but there's also the direct bond capability that can be done without electrical interconnect. And we're actually seeing quite a lot of applications and interest in just direct bonding technologies where there don't need to be necessarily any electrical connections, but it's more the transference of devices from one substrate to another. We have established a working relationship with SUSE Microtech, who has an engineering group at our facility down in Florida, and has been instrumental in helping us establish the operation of the XPS 200 bonding platform. If you're aware of the process flow that is utilized to exercise this process, it takes a number of different steps to do. You need to do surface preparation by CMP. Those surfaces have to be extraordinarily clean for the yield of that bonding process to be successful. You need to do plasma activation, you need to do hydration processes, you need to do alignment processes, you need to do bonding processes. For a lot of systems, for a lot of users, those processes happen in differentiated equipment sets. For the XPS 200, they're all combined into a single platform. So it greatly reduces the time for the process to take place, and it also improves the yield because you're not moving wafers back and forth in your fab between different tools and process modules. So that technology is being implemented at a 200 millimeter wafer bonding platform capability right now. You've seen before that this is a room temperature bonding process, so it really does improve things like alignment and CTE driven problem that you get from other packaging approaches. It does support high density interconnect at small pitch. The XPS 200 system is rated to 100 nanometers of alignment tolerance. So there's a lot of capacity and capability in that platform. Our tech transfer roadmap is due to be completed early next year, at which time we'll have an alpha process that's ready to start providing to interested customers. Looking forward, we see that technology expanding potentially into 300 millimeter capabilities. And we also have the option to expand into die-to-wafer hybrid bonding. I think that's something that certainly as we begin to start talking more about chiplet architectures, the die-to-wafer bonding approach for hybrid bonding is going to begin to start being a dominant technology, because bonding wafers will get us so far, but there are some constraints and limitations to that approach. So moving to a die-to-wafer hybrid bonding capability in the future is certainly the intent. Now, those three platform technologies are what Skywaters is working on today, but there are some other things that are important that I think are worth mentioning here in terms of the discussion of this larger ecosystem. And one of them is wafer bumping. It's a ubiquitous need in all of advanced packages, I'm sure you know. it really doesn't matter if you're using silicon interposer or you're doing hybrid bonding or what. At some point, you're going to be bumping into a interconnect level to put that down on a board, to put it down on an advanced laminate, whatever. And there is essentially no 300 millimeter capability here in the US today. Certainly none that's non-captive. And there are a few sources of 200 millimeter capability, but they're becoming fewer. And their limitation for being able to deal with 300 millimeter wafers and not having to core them down and expending the wastage that is that accompanies that approach. We really need to see more 300 millimeter wafer bumping capability here in the US. On the opposite end of the spectrum, if you start looking at smaller wafer sizes, different materials, GaN, gas, indium phosphide, those are materials that you need to be able to support at 4 and 6 inch wafers. And there's very little capacity for that as well. You're also accommodating in these processes some unique material sets in some cases. So there's really not a lot of capacity here in the US to support a growing ecosystem. It's another aspect of this problem that needs to be comprehended and addressed. We talked about the fact that you need a lot of different bump dimensions. You need WLCSP on the large side. You need C4 for flip chip applications. You need copper pillar for high density applications. You're probably also going to need some level of support still to this day for leaded solder alloys, particularly for space and defense applications. And you also need to incorporate some RDL capabilities because it's pretty common that you're going to need to do some level of redistribution before you bump a device. We talked about back-end processes and assembly and test as being an important part of this ecosystem. We're talking about things like wafer thinning and dicing, and that includes not just standard mechanical dicing, but also plasma dicing and laser dicing, temporary bond and debond, insort and final inspect. There are a number of US companies that offer these services, but we're going to need to look at having capacity expansion for these as this domestic market continues to grow. And the companies that are engaged in these AP and HI technologies are going to need very broad capabilities to handle varying substrate materials, thin die and die with fragile exposed structures like MEMS devices and sensors, for example. We're going to need advanced assembly capabilities. We need to be able to support all of these different components that we're talking about here as we aggregate them and put them together in multi-chip and chiplet modules. Interposer-based devices, stack device structures, all of these come with very unique material handling and assembly requirements. And they're going to need to be established for higher volumes. There's quite a bit of capability in the US right now for supporting those things at prototype levels, but how is this going to expand to be more manufacturable? How are we going to be able to automate some of those technologies? Testing, always a big problem. Wafer level test after fab or bumping to identify known good die prior to back-end processes is pretty standard right now, but what happens when we start doing chiplets? What happens when we no longer necessarily have the capability of testing the functionality of a device that has no bumps and very small interconnects? What about if we have hybrid bonded modules now? What do we do if we've got die on wafer stacks? These all present physical challenges to standard test methodologies. We also need to have the ability to do a wide array of reliability testing. Again, there are a number of companies here in the US that can support reliability testing today. And we need that capability to continue to expand because more customers are going to be looking to do more reliability testing. So I wanted to close here with a few keys that we see that are important for developing a domestic ecosystem for advanced packaging. First one is we need to develop broad consensus and priorities on the packaging technologies and capabilities that need to be established. I think that goes without saying, but everybody's going to have their own perspective about this. I think this is where some of the larger group efforts that are going on in the industry, like ASIC, like MITRE, are serving an important purpose because they're pulling together a lot of different perspectives from the domestic ecosystem. And everybody sees their challenges as the most important. But as we begin to start pulling all that information together and looking at that, it begins to start putting together a picture of where the biggest problems are going to need to be solved. We also want to make sure that we're aligning the government business engagement process and funding practices with commercial industry expectation and needs. I think over the last several years, that has changed quite a bit. It used to be that a lot of commercial companies just didn't know how to deal with FAR, didn't know how to deal with government contracting. That's changed a lot on both sides. I think companies have gotten a lot smarter and the government has made it a lot easier for companies to engage as well. One of the important things is, can we consolidate and forecast the government's full life cycle demand and technology needs? So we're aligning with the industry's forward-looking planning. I think this is a critical key. We're about to invest a lot of money in developing an ecosystem. And that ecosystem is going to support both government and commercial requirements. There's a real national security issue at play here, I feel, and making sure that the portion of this ecosystem that is going to support those government applications and that can be done with, where all parties can be financially successful is going to be a challenge. I think that's one of the things that we need to make sure that we're focused on is and understanding from the commercial side of things, from the manufacturing side of things that I would represent, understanding what those needs and requirements are going to be for a long-term engagement is a very important piece of the puzzle. We need to continue to expand existing and develop new pre-competitive public-private partnership organizations in workforce development and R&D and for design, fabrication, packaging, and test. The close work with academia and industry, I think, is well established here in the U.S. I think we do a very good job of that. Can we put now some facilities together that allow us to bridge over these valleys of death, so to speak, where new technologies are just not getting out of the lab, can't get into a manufacturing environment? I think that's a real important point of these public-private partnerships and the facilities that are going to be developed for them. We have a broad array of companies here in the U.S. that offer some of these capabilities, and leveraging those onshore assets and improving and expanding on their current infrastructure capabilities and their workforce to optimize the outcome, I think, is an important point. And can we develop some baseline metrics that are going to support accurate assessments of program-wide progress towards economic and security objectives and to highlight remaining gaps that may require other support? We're a month after the CHIPS bill has been signed. It's a 5-year horizon from now on. Sometime in that period of time, we're going to need to be grading ourselves on how we're doing on meeting the goals of this program. And where we identify a problem that I'm sure we're not going to see today, what options are there going to be to rectify that mid-flight in the program? Or will there be other opportunities to find additional program funds, for example, that can help identify solutions to problems that we're underestimating or that we're not seeing yet, or that economically begin to change due to other geopolitical or economic factors that are going to be developing over the next few years? So that's in my talk. I'm happy to take any questions, and thanks for your attention.